Hello, everyone. Thank you for inviting me to this VTC conference, workshop 10. I'm Joohyun Lee, who is an associate professor in Hanyang University. So today I will give a talk of this interesting topic of multi-agent reinforcement learning for a random access game. So this talk will be based on my publication on transactions on VQL technology with the same title. So this work is co-authored by my students Dong-woo Lee and Yu Zhao and Professor Jun-bae Seo from Gyeongsang University. Okay, so let's begin. So in this talk, we will solve the problem of random access protocol. So one of the famous random access protocol is slotted Aloha protocol. So the random access problem that this slotted Aloha protocol solves is that the time is slotted and several nodes transmit some packets to an access point. And in slotted Aloha, each node transmits a packet in a time slot with probability P. This probability may be equal across the nodes, or it could be selected for each node. But if you assume that each node use the same probability, then based on some probability theory, the probability that a given node has success in a slot is given by this equation of p times 1 minus p to the n minus 1, where large N is the number of nodes that transmit with probability p. So this is a probability that only one user, one given node transmits, and all the other nodes do not transmit. And if we sum up disjoint n events that such to compute the probability that any node has a success, we just multiply n or summate this probability n times to have this formula np times 1 minus p to the n minus 1. So if we have, let's say, 2 users, then the probability is p times 1 minus 2 times p times 1 minus p, and it is optimized at p equals 0.5. But in general, if we maximize this formula to find the optimal p that maximizes this efficiency, we can find that p star is equal to 1 over n. And at this point, and even or as n goes to infinity, this efficiency approaches to the number 1 over e, the natural number e, which is roughly 0.37. So the efficiency when n goes to infinity of slotted Aloha is about 37%. And we cannot get a higher efficiency in slotted Aloha. So the question that I want to answer in this work is, how can we increase the efficiency by using reinforcement learning? Okay, so we assume the same slotted system as slotted Aloha, but we want to change the policy using the reinforcement learning to achieve higher efficiency than slotted Aloha. So the goal of this paper is to develop a learning mechanism, essentially reinforcement learning mechanism for a random access game. So we want to maximize the system throughput or efficiency in a time-slotted uplink multi-user random access communication system. So we want to apply reinforcement learning. So I want to review a single agent reinforcement learning briefly. So three important concepts of reinforcement learning are state and action and reward. So state is the representation of the current scenario that depends on the previous history and previous actions. And depending on these states, the reward will be dependent on these states. And given the current state, this agent, and here a single agent determines an action, and this action can be drawn from some policy, and based on the current states, a policy determines an action probabilistically or deterministically. And the goal of this agent is to maximize the cumulative reward. And the reward, immediate reward, is given from given state and action. This reward can be random. And we want to maximize the cumulative expected reward over time. And to solve this reinforcement learning problem, the essential model that is used in the literature is Markov decision process. But if we only have one single state, in other words, if the action is not dependent on the states, then it essentially becomes a multi-bandit problem, which will be used in this work. So you can view this multi-bandit problem as a special reinforcement learning problem where you have only one state. In other words, you don't need to care state anymore in this multi-bandit model. So please see some literature or work on this multi-bandit to understand this work more deeply. So before I introduce the reinforcement model, to solve this random access problem, we designed a system model with this frame structure. So there are two steps of this frame model. We first have a subframe of several slots so the reason why we have this subframe is that we want to determine one slot in one subframe to transmit in some user. And we also define frame, which is a set of subframes such that we can regard the same number of slots in a frame for user across users. And one assumption that I want to make that to derive some algorithm and analysis is that the AP, this is a uplink scenario, and the AP knows in advance that the number of users in its vicinity is n, and the AP knows that this n is between n min and n max. Okay. And the number of slots in a frame is set to be the least common multiple of all the integers between n min and n max, such that we can divide this frame by the number of actual users and still have some integer number. This is designed to have a fair reward structure for users, which is not essential to run the algorithm, but for analyzing this problem better. And each frame is divided into subframes, and each subframe has the number of slots as k, where k is some number between n min and n max. Okay. And later, the action that each user can take is defined to be one specific slot in a subframe to transmit. Okay. So before we looked at single agent reinforcement learning, but here in this problem, there are multiple agents. So each node is defined as agents. So one naive approach to solve this multi-agent reinforcement learning problem is to have one central agent that collects all the information or states and define one central action and transmit that action to agents. But we want to use a fully distributed multi-agent setting, so that there's no control overhead between agents or APs. So the difference is that now we have different agents, and each agent selects or chooses its own action separately. So as an agent one, all the other agents' action will be regarded as the environment as agent for agent one. And here in our frame structure, we defined an action as a tuple of two numbers, k and l. And k is sort of the number of users, number of active users that is around, so that we can transmit the number of slots roughly proportional to 1/k. In other words, we want to have transmission probability equal to 1/k if this action choose some specific k. So the assumption or the idea is that this agent that chooses action k thinks that there are k users nearby. And then this L, the second number L, is it will be chosen between 1 and k, such that this is the sort of index of a slot in a subframe that each user selects. So here as an example, when we have k equals to 3, then the subframe, the number of slots in a subframe that this user thinks is 3 users. So it's ideal if these 3 users transmit at different slots. So the first action where L is 1 is to choose the first slot in each subframe, and L equals 2 is to choose the second slot in a subframe, and L equals to 3 means the third slot is chosen to transmit in each subframe. So ideally, if there were actually 3 users nearby, And if each user chooses different actions when k equals to 3, then that will be the ideal case that we have the efficiency of 1 if these 3 users chooses different actions. But in the beginning or initially, each user does not have that information. So it's not possible at the beginning, but we want to learn that having different actions across users. So to design, by designing an algorithm that each user sort of avoids the same action across users, we want to make the transmission strategy that each user chooses different slots across users. So to model this problem as a reinforcement learning problem, we now need to define the rewards. So because we want to maximize the reward, so we just want to summate the number of successes. So this I represents the number of successes in a frame. And we also want to avoid collision as much as possible. So we want to have negative reward of -c for each collision event. So the rewards, the immediate rewards that a user receives after one frame is defined as IR minus JC. So each time we have successful transmission, we add R, and each time we have collision, we deduct C from the reward. Okay. And before we introduce the developed algorithm, this multi-agent reinforcement learning framework is in general can be modeled by a game. Especially in this distributed setting, we can model this problem as a competitive game. And the analysis, the standard analysis that we take on this competitive game is Nash equilibria. So we analyze the Nash equilibria of this game structure. And we were able to find two types of Nash equilibria. The first one is pure strategy Nash equilibria, which means that each user chooses one action deterministically with probability 1. And that pure strategy Nash equilibria is such that each user chooses different time slot in a subframe. So that's sort of the ideal case that without any centralized entity or centralized scheduling, each user chooses different time slot in a subframe. So the efficiency becomes 1. So it sort of mimics centralized round-robin scheduling, which is a desired equilibrium we want to have in this problem. And the second type of Nash equilibria is mixed strategy Nash equilibrium, where for each slot, for action for each slot, we assign the same probability, and here we have probabilistic action that's a probabilistic strategy such that each action for each time slot is chosen with the same probability. And then it's essentially choosing each time slot with probability 1/k. Then this strategy sort of mimics the slotted Aloha at best, when the k is chosen to be n as the actual number. And now the rest is to develop an algorithm to achieve one of these Nash equilibria, and we want to design an algorithm that can converge to this pure strategy Nash equilibria using some learning algorithm. So now our goal is to design an algorithm that can achieve or converge to this pure strategy Nash equilibria using some learning strategy. So again, this as an agent, the task is to choose an action or two numbers K and L, such that the reward is maximized. So this problem as an agent can be modeled as multi-banded, because here we don't have any state concept, or there is only one state for this problem of one each agent. So we want to solve this problem using some multi-banded algorithm. And the algorithm that we take is so-called EXP3, or sometimes it is called softmax algorithm, which is an abbreviation of exponential weight algorithm for exploration and exploitation. So this is a very classic algorithm that can solve a general multi-banded problem. Okay? And because this multi-agent setting is sort of adversarial setting in multi-banded, so it is well known that a banded algorithm performs well. The banded algorithm that performs well in adversarial setting is EXP3. So we take this EXP3 algorithm as the as our algorithm. Okay. So to describe this EXP3 algorithm, I first need to define this Q function, which is discounted reward in the history. Okay, so in our work we use moving average of success probability in the history, or success probability or reward in the history. So this Q represents or proportional to the previous reward we had for specific action A, and we use moving average because recent reward is more important. So using that moving averaged reward Q, we will determine the probability or a probability to choose on action A. Okay, so action A is a tuple of K and L, and for each action, the probability that we will choose is proportional to this exponential term in the numerator. So this probability, this assigning probability, is proportional to exponential of eta times Q and AT. So you can see that this probability is proportional to the exponential of Q. So as you have higher Q, the probability to assign to this action gets exponentially higher. Okay, and this parameter eta is defines how we assign assign the probability to higher Q. So it determines the degree of that allocation. Okay. So as you have larger eta, this probability concentrates more on the higher Q. And based on that probability, the action is chosen probabilistically, and based on the actions that are chosen for each user, it runs the random access game for one frame. Okay? And then updates the reward in the moving average fashion. We will multiply discount factor gamma to this Q. Okay? And by using this learning algorithm, what happens with high probability is that when the actual number of user is 3, then as we envisioned, it is with high probability each user chooses different slots in a subframe, because the fact that the other users choose different slots, the remaining slot will give you higher reward, so that each user sort of tries to avoid the same slot number that other users have already chosen. Okay, so essentially the learning algorithm sort of converged to the pure strategy Nash equilibrium. And essentially at this pure strategy Nash equilibrium, we have some throughput of 1 after some frames. So this is the result, and in the red graph, you can show that EXP shows the best case. And as benchmark, we tried 2 more bandit algorithms. The first one is epsilon greedy, and the second one is UCB, or upper confidence bound. But we found that EXP3 is the best among these 3 multi-bandit algorithms. And we want to have a better efficiency than slotted Aloha, but initially, because we don't have any reward information at first, so the initial sum throughput or efficiency is on average it's the same as the slotted Aloha, but as time elapses, the sum throughput increases as the users learns the pure strategy Nash equilibrium strategy. Okay, so we count the number of average rounds or frames that is needed to surpass some target throughput of 0.6. Okay, so in our simulation, when the number of user is 2, EXP3 can beat the average throughput of 0.6 in just 4 rounds. And even when the number of users is increased to 6, the number of rounds required to beat 0.6 throughput is only 11 for EXP3. It's higher in epsilon greedy, which were 7 and 26. So although we need some initial learning periods to achieve desired probability, so one nice thing is that even at the beginning, it's the same as the slotted Aloha, but later on, the sum throughput increases very fast and almost approaches to 1 after 100 rounds or so. And the benefit of the learning algorithm is that a learning algorithm can adapt to environmental changes. So to model this environmental changes, we change the number of users in the first phase and the second phase. And this new user joins the system after 5,000 frames. So right after this user joins the system, the throughput decreases because now the environment totally has changed. But after a few frames, it learns or adapts to the environment to change the action, and later on it approaches to the higher some throughput even in changed environments. So this is why we adapt moving average reward to adapt to environmental changes. So even in non-stationary environments, our algorithm can adapt to that environmental changes. Again, the performance is the best for EXP3, and then UCB is better than epsilon greedy, and epsilon greedy performs the worst, but still epsilon greedy still learns and achieves higher throughput as time elapses. And another simulation we had is that we may have different priorities. So maybe one node may have more important application. So depending on that different priorities, we can assign higher reward per collision, so that this user with higher priority can aggressively send packets, and we can show that the average throughput for higher priority user shows higher average throughput. So our algorithm is so in our algorithm, we can use different priorities for different users. When QoS of some specific applications are important, our algorithm can also solve the situation. So as a conclusion, in this work, we formulated slotted random access system as a random access game. And we have shown that this random access game has pure strategy Nash equilibrium and mixed strategy Nash equilibrium. And to achieve the pure strategy Nash equilibrium, we propose EXP3, which is a popular algorithm in bandit problem. And EXP3 based multi-agent reinforcement learning algorithm is proposed in this work. And our simulation results show that each time slot can be fully utilized at pure strategy Nash equilibrium, which can be achieved by our EXP3 algorithm with high probability. And this EXP3 algorithm is better than epsilon greedy and UCB in our simulation. And also we showed that our algorithm can adapt to time varying or non-stationary environments with moving average reward. As a future work, we want to investigate how to set learning parameters such as eta in EXP3 and gamma, the discounting factor in moving average reward. And that's one problem we want to solve in the future work. And we also want to mathematically analyze the regrets of our EXP3 based algorithm, which is the usual mathematical problem in bandit literature. And we also want to investigate the convergence rate or convergence speed to the pure strategy Nash equilibria that can achieve the maximum throughput. And since in our work we assume that n min and n max sort of the lower bound and upper bound of the number of active users. So we assume this algorithm, but in our future work, we want to design and use the algorithm for estimating Nmin and Nmax. And our system model is very basic, so we want to extend to more extend our game model to a more realistic and practical random access scenario, for example, with multiple preambles. So thank you for your attention. And if you have any question, please don't hesitate to send me an email via joohyun@hanyang.ac.kr. And for more details, please see our paper, Multi-Agent Reinforcement Learning for a Random Access Game, appeared on IEEE Transactions on Vehicular Technology. Thank you.